so you should be really good at it. But also, more importantly, it's a nice short class period, and that makes it perfect. We should be done by the end, and you could probably just have practice, which is what's going to happen. I'm going to give you a bunch of practice just so you guys get the vocabulary down. The idea about rotational kinematics versus translational kinematics is that we're talking about things that are changing their direction, not changing their location. Translational kinematics refers to something that's going to change its location. It's going to go from one place to another. We already know all about that. We have delta x, vi, vf, a, t. And we're looking at, the idea that we're dealing with a constant acceleration. You should probably have in your memory banks 5 motion equations that we used to use for this kind of garbage. Again, assuming a constant acceleration. You may want to pull those up, have those in front of you. So I'll take a minute. If you have those, great. If you don't have those in your notes or you don't know what they are, copy the kid next to you. 3 of them are on your equation sheet, but you're going to use some. And so it might be in your best interest to get those out now. And you might want a calculator too. Think it's not too big a stretch, right? Delta x was our displacement. So for something that's rotational motion, we'd say delta theta, the change in angle of the object. And you guys said that was 56 and a half rotations. We measure delta theta in rotations or radians, not degrees. Degrees are for angle measures where we use sine, cosine, and tangent, where there's a triangle involved. But for anything else, when we're talking about any kind of motion, we're going to use rotations or radians. Everybody understand? The word revolution might also get used, but I tend to say rotation or radians. So it'll be pretty clear. They'll tell you. So it's one of those two. This particular measurement was in rotations. We can all probably agree that the final velocity was 0. We didn't have, or we don't know, the initial velocity. We're going to use the Greek letter omega, which is just W, for initial and final velocity. These are the angular velocities. Generally, these are given in RPM, or RPS, or radians per second. We talked about this first semester. I'm just reiterating it again now. When we talked about centripetal motion, this came up. We're going to use the Greek letter alpha for angular acceleration. And that will almost always be radians per second squared. So unless you're asked otherwise, that's the unit you should give the answer in. And in this problem, time is time. Whether you're dealing with something that's in translational motion or rotational motion, it's just a variable for how long it took to do something, and we were at 1 minute and 24 seconds. So 1 minute, 24 seconds. All right? So here's what I want to see. I'd like you to find the initial velocity that I spun the wheel in rotations per minute. And I'd like the angular acceleration in radians per second. I'm of a mind I don't need to teach you how to do this, that you have a set of skills already. And all I'm doing is reminding you of your set of skills. So again, that's what I want. I would like you to tell me the angular acceleration in radians per second squared and the initial velocity of the wheel in RPM. I'll come around and see your answers in a few minutes. So, although many of you have what is the correct value for the units that you left your answer in, you didn't put them in the units that were specified, and that's going to be a part of this. So let's start with finding the initial velocity. I think that's a good place to begin. I used this relationship, and I noticed that many of you did as well. Is this the relationship you used? Good place to start. Good place to start. If you're using this relationship, I would put everything in the units that you either want to have at the end, or you need to put everything in the same units and then convert at the end. I decided to put everything in terms of rotations in minutes. 24 seconds is 0.4 minutes. So this is 1.4 minutes. I did 24 divided by 60 and added 1 to it. You don't have to do everything in seconds, especially if you're asked for your answer in minutes. RPM, rotations per minute. So although a lot of you converted that to seconds, it's fine. It's not what I asked for. It would have been 84 seconds. This is going to be 56.5 equals 1/2. Don't know this one, but this is 0. And this is 1.4. This gives you like 80 rotations per minute. Let me narrow it down. I got 80.7 RPM. A lot of you got 1.3 rotations per second. That would be the right answer in rotations per second. You did everything right. You just didn't put in right units. Now, got to be honest with you. Do you know how to take this and convert it to rotations per second? If you don't, I can train you. You need to be able to. Do you need training? Okay, so you'd like to learn how to do that? I will show you how to do that. We'll do that right now. I asked for it in this unit. But let's say that I actually wanted you to give it to me in radians per second, and you have your answer in rotations per minute. I am a unit multiplier kind of person. So if you need to know how to convert, perhaps put a small aside in your notes and put in, here's how you convert. In fact, at the end of this, we're going to convert radians per second squared to rotations per minute squared, because I don't know how you guys do something that's squared. And the history suggests you guys don't know how to do that. So let's do a conversion, real simple, straightforward. I want to convert 80.7, and I write it as a fraction when I'm doing a conversion. I hear from students all the time, I don't know whether I'm supposed to multiply or divide. So look at unit multiplier. You want to convert rotations to radians. So what side is rotations on now? Rotations is on the top, right? That's what's on now. So we want to put rotations on the bottom in our multiplier, which leaves a spot for whatever else you want to convert to. Now, your conversion fact, it should be obvious. You should know how to use a conversion fact. You should know where the 2 pi goes in this conversion fact. For every 1 rotation, 2 pi radians. That's your conversion fact. You do this, you never have to ask yourself if I'm supposed to divide or multiply by 2 pi. Right? It'll be clear and obvious. But you also want to get rid of that minute. Put it in seconds. Well, minute is currently on the bottom, so I'm going to put minutes on the top. That will cancel out the minutes. The open part there, I can put hours, seconds, days, whatever you're trying to convert to, that's what goes in the other spot. We're putting seconds. That's what we want. Your conversion fact. You know which one has to have the 60 and which one gets the 1. So never should I ever hear you say, I don't know if I'm supposed to divide or multiply. All right? Unit multipliers do that for you. All right? Now, we were also supposed to find the angular acceleration. I would have chosen a relationship that probably has those things in it now that I know the initial velocity. But let's do this the old-fashioned way, which is me saying use what you are given in case you made a mistake solving for something, and many of you did. Now, I wanted my answer in radians per second squared. So I would have converted everything into seconds and radians to do that. Okay, that's what I would have done. That just means converting this to radians, because we already know that this is 84 seconds. That's pretty easy. But I want to show you how to do a conversion where something is squared. So I'm going to leave this in rotations and minutes. Everybody understand? And then we'll convert. So this is 0. So I get 56.5 equals negative 1/2 alpha times 1.4 squared. I actually didn't work this out this way, so I need to do this. So 56.5 times 2 divided by 1.4 divided by 1.4. I get that alpha is equal to negative 57.65 rotations per minute squared. Now, we need to convert this to radians per second squared. Have you guys learned how to do that when you have a squared as one of your things? Anybody do this before? Okay, so this is the first time? All right, we're going to do all the same things. Negative 57.65 rotations divided by 1 minute squared. Unit multipliers. Let's handle the rotations. That one's easy. Rotations, radians. 1 rotation, 2 pi radians. That one's easy. We want to convert minutes and be left with seconds. So put minutes here, just like before. It goes on the top. Seconds goes on the bottom. Put in your conversion fact. There are 60 seconds every 1 minute. But we don't have minutes. We have minutes squared. You just square your conversion fact. That's all you do. You square the conversion fact. So, all right, from one to the other. It's not going to be just one of these. It's going to be both of these. Do you remember from first semester how to go from one to the other? Should I take your silence as a big no? Well, it would be this. If delta x is on this side, it equals delta theta times r on that side. We didn't do that one first semester. We did this one first semester. Because we converted from angular to linear during centripetal motion discussions. But there is a way of converting a linear value from an angular value, or vice versa. It shouldn't be too tough to figure this part out. If an object rolls, it rolls 1 circumference every rotation. That's where this comes from. That's where the whole circumference equals 2 pi times r comes from. Right? 2 pi is 1 rotation. R is going to be your radius. The only thing is, to use these conversions, these have to be in radians. Have to be. Let me show you what I expect. A 20 centimeter ball rolls down a 5 meter ramp. It takes 4 seconds to get to the bottom. How many rotations does the ball make? And what's its linear speed at the bottom? What's its angular speed at the bottom? Ask any of these questions. Those are a kinematics question you have to be able to do. Again, a ball just rolls down a ramp. Stupid problem. Again, I think the stuff is stupid anyways. It's boring. But the question is going to be, when the ball makes it to the bottom, how many rotations did it make? How fast is it spinning? What's its linear speed? Those are all the kinds of questions that you should be expected to be able to answer. So how fast is it spinning? What's the final angular velocity? What's the final linear velocity? How many rotations did it make on the way down? Now, again, it's everything you've already done. There's nothing new here. But suddenly, there's twice as much information. So you got delta x, vi, v final, a, and t. And you have delta theta, omega I, omega final, alpha, and t. These things are connected because it rolled. Look at all the things you were given. You were given that the initial velocity is 0. So that's a 0 in both places. The linear displacement was 5 meters. The time, 4 seconds. Got to figure out everything else. How fast is it going at the bottom? How many rotations did it make? What's its linear speed at the bottom? This is the kind of stuff I'm going to expect we can do. Based on me walking around the room a minute ago, it seems like you guys could do this. Could you? Can you start it now? Do you think so? Or do you need me to do it? I don't want to do it. You can do this one right away. Because you know the radius, 0.2 meters. The problem is that your answer will be in radians. You got to keep those things in mind. I want to do that one first. Delta x equals delta theta times r. We can figure out how many rotations it makes without knowing any other kinematic stuff. It traveled 5 meters. Delta theta times r, which is 0.2 meters. Now you got to divide your 5 meters by your 0.2 meters. Bless you. That gives you delta theta. That's 25, and there's no unit there, right? The meters cancels. What unit must it be if there's no units? Radians. That has to be radians. So that can't be your answer. Because you're asked to say, how many rotations did it make? So although you have an answer and everything you've done is correct, that can't be the answer you give. You'll need to convert that to rotations. This stuff is hard because of all the little particular things. Can you convert that to rotations? I hope so. It's just divided by 6.3. It's not tough. But again, it's a little stuff. How much longer do we have for the bell rings? Mondays, I never know the schedule. 6 minutes. All right, give it a try. I'll put the answers up on this in just a minute. But see, can you fill out everything? And let's make it tough. I want this in RPM, so we get the full effect. I want this in radians per second squared. These will be in meters per second squared and meters per second. I'll put all the answers on the board right before you guys leave. You need the practice. And if you're having difficulty, you should get me over there so I can help you. All right? So those are all the answers and the units that I wanted them in.